Hello, this is Andy Schweitzer, and this is getting close to wrapping up the end of our combined gas law, states of matter of gases. So, um, we should understand that gases are small particles that travel very fast. As we raise our temperature of these particles, they move faster, therefore putting more collisions on the outside container, the inside of the container, either increasing its pressure or increasing its volume. So this video is what's called the combined gas law, and we want to look at the mathematical relationships between all of these variables, whether it be temperature, volume, and pressure. The units I'll use for pressure, you can use any unit you want. Now, for all of these things, units, you can use what you want, as long as it's an absolute scale. So we can use millimeters of Hg as a unit of pressure or atmosphere as a unit of pressure. We can use volume as a unit of pressure. I can use, so volume would be, let's say, would be liters, milliliters. It doesn't matter as long as I'm consistent. Temperature, however, you have to be in Kelvin, and I'll show some examples of that in a moment. But we will not be dealing with number of particles. That is going to be constant. Okay. Two types of containers that we'll often deal with in this particular chapter in gases is either a rigid container or a container that's allowed to expand or contract. And that's important in the grand scheme of things. So if I were to have, let's say, a rigid container here, then the volume is constant. Okay, as opposed to if I have a balloon, in this case, this volume is allowed to expand and contract. But to be honest with you, a balloon, the pressure is constant. So the pressure on the inside of the balloon equals the pressure on the outside of the balloon. This was kind of outlined in a previous video, but we'll look at some of the mathematics here as we move along. So in this case, for a rigid container, you should understand that there are particles that are bouncing off walls inside here. Every time a particle hits the wall, it creates an impact, which creates a force on the outside of the wall. Force is equal to, or I should say, rather, pressure is equal to force per area. And often I replace force with collisions. Collisions per area. The more collisions you have per area, then the more pressure will be inside that container. But either way, you should note that if you increase the temperature, you will increase the movement of those particles, and therefore you'll increase the pressure, or I should say, yeah, equal pressure. Okay. Conversely, if I were to lower the temperature, I would lower the number of collisions if we're lowering the pressure. There is a mathematical relation between this. This is a linear relationship. Pressure 1 over temperature 1 equals pressure 2 over temperature 2. This is a very common mathematical relationship. It is linear. It's a proportion. So the other one here, now in this case, you should note that as I increase my temperature, right, particles in the balloon start zipping around, bouncing off the walls at a greater frequency because they're moving faster. The particles inside here, as they make those collisions, create, again, a larger number of force per area, which causes the pressure inside the balloon to temporarily increase. This increased pressure causes the balloon to expand. Okay. Now, as the balloon takes on a larger volume, there's more surface area. That will cause the area to increase. And then the number of collisions per area returns back to its original pressure, and the pressure inside, once again, equals the pressure on the outside. So eventually, if the pressure inside is greater, it has to expand, or vice versa. So in this case, the increase in temperature caused an increase in the volume. All right, so, or a decrease in temperature would cause a decrease in volume. This is also a linear relationship, which is going to be T1 over, I'll back that up a second. It's going to be P1, pressure 1, over temperature 1 equals pressure 2 over temperature 2. Another relationship. Okay. Given there's 4 variables, given 3 of them, I could find the 4th one. All right, and finally, we're going to look at a relationship between where temperature is held constant. Now, in the previous ones, we had the volume is constant in this guy, the pressure is constant over here. So now it's going to be temperature's chance to be constant, and we're going to look at see how pressure and volume interrelate. This is a pretty common scenario where we would use a piston, where you have a car, engine, or anything of that nature. Very often we'll see a piston situation. So we have a little circular cylinder with a closed bottom. I'll have an open top, and I'll have a piston coming in here and basically reducing our volume. You have a certain number of particles flying around in here, and again, pressure is equal to collisions per area. So if I were to reduce down my volume for a given temperature, particles moving the same speed, I am basically reducing my area, and then therefore my collisions per area cranks up my pressure. So as I reduce my volume, I should be increasing my pressure. Again, if I draw that same picture here with a smaller amount of area to that right there, then all these particles in here are trapped in a smaller area, and the collisions are traveling the same speed, but there's less area, so there's a larger number of collisions. This is not a linear relationship, it's a reciprocal relationship, which we've talked about in the past as well. P1 V1 equals P2 V2. If I cut my volume in half, my pressure doubles. So it's a reciprocal relationship. Okay. Now, we put all 3 of these things together. We have what's called the combined gas law. And I'm just going to click onto a new page here. And the combined gas law would be P1 V1 over T1 equals P2 V2 over T2. So we've combined each of these together. I have a total of 6 variables here. Just a note, this guy has to be in Kelvin, always. These ones can vary as long as you're consistent throughout the chemical reaction. If something is constant in this particular example, then it would just drop out of the equation. If temperature is constant, then this is gone. It just stops one. And that's pretty much it. Given all of the variables except one, you simply solve for the missing variable. Here's an example here. Let's say we take a balloon, okay, and let's say this balloon is 1 liter in size, okay, and let's say it's at 25 degrees Celsius. I take this balloon and I crank up the temperature to, to 50 degrees Celsius. Conceptually, you should note that it should increase in temperature. The pressure on the inside, the atmospheric pressure, is here, and it would be the same as in here, as the same as here. The pressure is not changing in either balloons in the end. And of course, as we're looking at these relationships, you look and see 25, okay, and then 50. Always thinking conceptually, mathematically, you think, okay, well, my temperature doubles, maybe my volume should double, and that is a very good mathematical linear relationship to utilize. But the question is did my temperature actually double? Okay, and the answer is no. I went from 25 degrees Celsius to 50 degrees Celsius. This Celsius, 25 plus 273 equals 298. And then this guy is going to be 273 plus the 50. All right. And this is going to give me, running out of room here, 323 degrees. So I have 298 Kelvin going to 323 Kelvin. So in reality, number-wise, I increased, but not that much. If I went from 300 to 600, I would double my volume. So let's set the mathematics up. P1 V1 over T1 equals P2 V2 over T2. Now I'll tell you, pressure is not changing. A lot of times the problem just won't discuss it. The pressure is the same on both sides. You could put 1 in here if you want, and it'll just cancel out. The volume initial, 1 liter. Temperature initial, 298 equals the volume 2. Oh, that's what I'm looking for. I'll leave that in there. Temperature 2 is 323 degrees Kelvin. All right, and you solve for V2. And you should expect it to get bigger. Is it going to double? No. In fact, it's going to get bigger, but just not a whole lot. Just some. I'll grab my calculator here, and I will get the exact answer. Again, as you look at the mathematics in your head, you should have some idea how this is going to run out. I should be 1 liter, maybe a little more than 1 liter, not much. 1 times 323 is 323 divided by the 298, cross multiply divide, and I get 1.08 is my V2. So at this point, 1.08 liters. All right. Again, it's simple as that. Plugging values into a mathematical equation and solving for an answer. Thank you very much.